So today, actually, me and my colleague Kyle, we're going to present our ongoing work. As you see, the name is called PyELM-MME. It's a big title, but I'm going to explain bit by bit what is our goal and what is our aim and what we have right now and what's the future. Let's start with the goal. The goal is like making a IPython or Jupyter notebook for making a multimodal ensemble using the latest machine learning methods. But may not be these things are clear to everybody in this audience because we are actually from more on the climate prediction fraternity. So that's what we start with the concept, like what does it mean by multimodal ensemble and what the machine learning we're going to use it, and then the tool part. So I'm basically covering the concept and a little bit of research, and Kyle will present the tool part. So coming to the multimodal, like what's multimodal, I start with the model. Generally in the machine learning, when you see the multimodal, it's basically like different kind of machine learning models. But today we're going to say it's actually it's on a climate model. And there's a different kind of climate model. Some climate model give us a projection for next 100 or 20 years. Some models, which call general circulation model, which give us a prediction for a couple of months. And we're talking about that kind of model today. So it's basically a set of computer code based on a fundamental law of physics. And basically, it's divided the whole sphere of the globe in different grid, and every grid, they calculate all those things. And this is like a state of art prediction system, comparing the typical statistical data analysis kind of prediction system. So the thing is like, okay, so we have a model, but why we need multimodal? So with a great improvement in the physics side, we have a lots of model nowadays. So that's really good to have so many predictions. But there is some a kind of a silent, salient problem with that. For example, I just bring up an example like let's say we're in 2009, almost 10 years back, and in May, and we're trying to see like what's the forecast over summer monsoon over India. And that time we have like 5 or 6 models which is in real time, and we got that type of forecast. So imagine you were in May and you were trying to predict for next season, which is June to September, and these are the information you got from different modeling system, but to whom to believe? So that is why we need a system to make it like combining or multimodal. So for example, this is the observation happen. So if we compare those observations for each of the models, it's like, we don't even know like which one is good, which one is bad. Some model capture the scanty part over the northern part of the country, some model capture the wet part, but some model underestimate some area, overestimate. So the main purpose of the multi-model is actually to improve the skill of individual model. So that's the whole purpose. That's why like we need a multi-model. Now the question is like how can we make multimodal? The simple thing is like, in a statistical sense, you just make the average, or we said equal weight. The another way, which is very popular in our science, is called weighted multimodal. It's kind of basically doing a multiple linear regression, but those weights calculate based on their prior information. So that means these models actually run for last 20, 30 years, and you have those sample data set, and you make a combination of model based on the linear regression and giving those weights calculated from those equation, and store those weight and then multiply those weight in a real-time forecast. So that's the way most of the climate modeling system doing this thing. But we're thinking about, can we implement a machine learning on this particular method? Because this is basically a regression method. So you can use the machine learning for this kind of regression. So basically, like here, our input layer should be the output from the GCM or climate models forecast, and our output will be the actual the observation. So we just thinking about like pictorially, like we can actually have this kind of network. But there is a potential limitations, because as you know, the machine learning or any kind of statistical sophisticated model need more data set to train properly. But we have a bigger limitation, which is like a sample size, because those model cannot, like we don't have a model forecast from last 100 or 20 years, because these are very state of art new models. They might have some 30 or 40 years, which is again not sufficient for any kind of a deep learning or machine learning. So that's one of the limitation of the study. So that's what we start with, a very simple approach. Like, let's start with a single hidden layer feed forward. Like, we don't need like so many hidden layers. We like just make it a simple network to start with the work. So on that note, there's another limitation, barrier, because like single feed forward have some potential problem, just like a long computation time, over tuning. So sometimes we have a prediction with a highly over tuned or overfitting. For that, we go more kind of a next step to select which method we can actually go for this problem. And we found like a extreme learning machine, a new method. It's called generalized single layer feed forward. It's actually developed in 2008. uh, the difference between this and the traditional SNF is like, for this neural network, we don't need to tune all the parameters. I'll come on that step by step. Just let you know, like, this is a different way to see it, and it's developed by Huang in 2008. And he explained that the extreme means to actually move beyond the conventional artificial learning and to move toward like brain learning kind of things. And like, in a nutshell, I can say like it's a simple math, but it's enough. And it's actually like far away faster than the single fit for a neural network. So that's what we choose it, because we have like a problem with the sample size. So we should not go a very sophisticated modeling. So that's what I choose this ELM for this problem. Now come back, like, why it's first. Just give you a little bit of information. Like, actually it's a semi kind of system. Like, the first layer, which is from input to hidden, that was like randomly generated. Like, for example, the weights of the each nodes and the bias is like randomly generated. It's not actually following the backpropagation system. First it's randomly generated, then it's all the calculation, all the train is actually between the hidden layers and the output layers. So if you just think about like making a equation, you think like this. This is actually a linear system between the hidden layer and the output layer. And here, like, the weights and the bias, which is wi and vi in the first layer, is actually randomly generated by the system. And then basically once you have those value, it's become a linear system. But it has some problem with the matrix invertible. That's why we use the Moore-Pensar G-inverse to calculate those beta. If I just explain a little more and just giving you the more sense, like how the learning algorithm starts. So it's, again, it's like randomly assign the weights, then calculate the hidden layer output, and then basically a simple system of matrix multiplication to calculate those beta. So that's what, like, very easy, and in my sense is a very white box kind of model. Like, we know exactly what's going on inside the model, because again, this system is actually for the real time forecast. So we should understand what's going on. Otherwise, like, we should have a different kind of forecast for every year, and we don't know how to explain it. So on that, we actually like long back, like in 2014, I published a paper on like to understand whether this method has any added value over the simple method. And if I just explain you a little bit of this result of that paper, like, this is a box plot of the observation from last 20, I think 30 years, and all the prediction system by ensemble mean, which is like just average of the model, then multiple linear regression and the ELM. And you can see like the ELM actually captured the spread or the interquartile range, and it's far better in terms of the variability compared to the observation and the other model. And we also calculate some kind of a skill score, and mostly like a bias based skill score or correlation based skill score. But in every case, as you can see, this system is actually outperform of the like existing methods. So on that, like, we have a proof on the scientific point of view. But the thing is, like, although I explained very easily, but it's for a non-data scientist or non kind of a statistics just a background cannot do those kind of things. So when I wrote this paper, I basically working in a MATLAB, and it's a licensed software. It's not easily available, and nobody, like, it's very hard to code in the MATLAB if somebody don't have the background. So on that, actually, I invite Kyle for this problem, and Kyle is a very good Python programmer, and start brainstorming and thinking about, can we have a tool for this kind of method? And that's what we actually having this method, PyELM. And here I'm going to mute, and Kyle, please go ahead.
Thanks, Nachiketa, and thanks everyone for the opportunity to share about this tool. Yeah, so how do we operationalize multimodal ensemble forecasting with ELM. We've made a tool called PyELM-MME. It's designed to be incredibly flexible and robust, and especially user-friendly to eliminate the barriers of entry to climate science and climate forecasting for novice programmers and non-data scientists. Our tool is based on a Jupyter notebook. It's implemented as a Python package, and then we've implemented some standard use cases in Jupyter notebooks. PyELM-1D works with like either spatially aggregated data or like single point data, and PyELM-2D will work with spatial data over a latitude and longitude range. We've implemented ELM and ensemble mean and multiple linear regression just to have some benchmarks for comparison. Nachiketa, if we could go to the next slide. This is kind of the data flow of PyELM-MME. User will provide a training data set, which will include GCM hindcast data for however many years they can get, historical observations for each of those years, and then we will use PyELM-MME to build the relationship between those. The really good thing about PyELM-MME is that it automates all the simple but frustrating tasks that are required to use like traditional data science utilities in Python, like scikit-learn and HP-ELM, which is the library that implements ELM that we're using. We take care of the reading and processing and cleaning, the data storage, all the like array manipulations and dimension reduction and things like that. So the user can get straight to the science. Yeah, we've implemented some custom data structures for storing the different training data and forecast data. The multi-model ensemble is where all the action happens. We've implemented numerous convenience functions to allow the user to use the same function interface to interact with many different external data science utilities. So that makes PyELM-MME like easily extensible to other statistical methods, like potentially in the future we'll add like single layer feed forward network or convolutional neural network, things like that. Once you've added the data and pre-processed, you can compute cross-validated hindcasts using like a leave in out method. So leave out 3, leave out 5 years. And then we also take care of the data visualization and skill measurement for you. We've added some methods for plotting using matplotlib, which is a commonly used Python plotting library. You can examine like a timeline of the hindcasts, anything else like that. Yeah, and then you can also export the data. So my background is in data science, and I recently transitioned into the climate science realm. And going from a novice programmer to where I am today, I've learned that it is a giant pain to manage all the packages and things like that you need to do this kind of computation. And so part of the big benefit of PyELM-MME is that it's distributed on Conda or anaconda.org. So you can install our code as well as all of the dependencies with one command in the terminal, conda install, and that's our conda channel right there, PyELM-MME. That'll allow you to access the PyELM-MME library as well as the Jupyter notebooks, which are implemented as there's 2 entry points into the thing called PyELM-1D and PyELM-2D, which you can just enter as a simple command in terminal, and it will bring you straight to the user interface. The goal from my design was really to keep it very easy to use and eliminate all of the headache of installing and managing packages and compiling code. And so this has a huge benefit to novice programmers and uh, climate scientists who aren't the most skilled at you know, coding necessarily. Yeah, if you could go to the next slide. So this is what the tool actually looks like. It's probably familiar to a lot of you. This is a Jupyter notebook. You start out giving it your a path to your training data and your forecast data, as well as some switches to tell the program what the format of your data looks like. And then you can next give it a list of methods and skill metrics you want to use. Right now, we're only implementing ensemble, mean, multilinear regression, and ELM. So that's all. But in the future, that list will be expanded. After that, you have to provide the arguments, which are parameters for defining the different like meta design of each statistical implementation. And then we'll actually take care of like this next part. We'll read the data using the reader class, load it into an MME object, and then use this convenience function called train MMEs to train and store internally the results of the cross-validated hindcast using the different methods, as well as using models. And then the plotter class implements all those plotting functions that we talked about earlier, such like the timeline that you can see here. Nachiketa, if you could go to the next slide. Yeah, so we've also we got the plotter's skill matrix function, which allows you to examine the numerical values of the different skill metrics for each model and for each multi-model ensemble methodology, which is very useful. You can also use that in the 2D. For the 2D version, you can plot skill. Yeah, thanks, Nachiketa. Plot skill as like a map, but you can also examine an individual latitude and longitude point by passing the point keyword into the timeline function, or the skill matrix function, or bar plot function, box plot function. It's really useful for examining, like, for say a particularly problematic area, if you have a specific geographical area that might be of interest. Yeah, Nachiketa. Yeah, thanks. So in conclusion, we hope that this tool will lower the barriers to entry for climate scientists, or to climate science, for climate scientists and for novice programmers. And it works on any time scale. We will be implementing more in the future and improving performance in the future as well. Thank you so much.
Yeah, just to add, like as I mentioned, like this tool is like the simple thing, like it can be customized very easily. So it can be actually customized for the subseasonal focus, which is like currently everybody is looking for, and also like it actually can differ a number of other methods. But again, like we have to think about the sample size, so we cannot actually add like 1,000 machine learning system. But the thing is, like, it's a very interpretable machine learning system, and it's very like in terms of the mathematics, everything is very white box kind of things. And also the what Kyle said, like it's like somebody should just to have to use, don't worry about this thing. But if somebody wants to add, if you look the Python code, it's very simple. Like somebody can add anything if he knows the background. On that, I said thank you very much for listening, and please give any feedback. And this is actually up in the GitHub, so anybody can download it. I can also write the function, I'm sorry, the address in the chat. Thank you.